Hello everybody! I hope everyone's having a wonderful day. So today we're going to be talking more about double hashing. In particular, we're going to be finishing up our hashing topic today. We might talk about something new. We'll see. So just as a reminder, remember double hashing is a type of open addressing collision resolution where what we do is we are going to use a probing sequence. Remember, think of the little bunny that wants to get to its nest, has some cabbage or something, wants to go to the nest. The whole idea is that it takes little hops. Now, we've realized that when we take little hops, we can form these clusters which create and degrade the performance of the probing sequences that we're using. So what we're going to do is a secondary hash function that takes bigger steps that can vary. So they can be bigger, they can be smaller. The whole point is that they're of different sizes. They aren't just one little step. Remember, think of the bunny wearing the rocket boots. So one that will jump all the way from here to there, or it might be take a little step. The point is that it takes a step. It just might be of different sizes. Now, remember that Q is prime and M is prime, where M is the size of the table. Q is just the one that appears in our secondary hash function. So remember, H of K is called the primary hash function. This is the secondary hash function. The idea is we're using the secondary hash function to operate and use these little steps. Okay? So just to illustrate, because really I'm just going to be giving you effectively the same algorithm again. I'm going to show you how what the algorithm for what would look like, and you'll notice it's basically the same as the other one I showed you the other day. The only thing that's a little different is the probing sequence. So input, output. So these are just the same as they have been for put. Okay, the position is going to be where I give the primary hash function. I'm going to hash into the table that, and I'm going to have C to be my counting variable. That's going to count how many hops I've done. And then all I do is I have to determine if there's any duplicates, so I can't skip over any of those deletes if we use lazy deletion. So keep in mind, like I said, you can modify this to just get to make sure that it does exist. If it doesn't, then you can proceed with this, and you can make this go a little faster by including those deletions. But however, it's still going to have the same worst case time complexity. However, you might be able to deal with those lazy deletions a little bit better. Regardless, asymptotically makes no difference. So while some pause is not equal to null, we do the following. So remember I need to check for duplicates. So if t sub pause dot get key is equal to k, then what? If I get a duplicate as I'm performing my adventure through the table, I want to make sure I catch that. Otherwise, I'm just going to apply the probing sequence. You'll notice it's quite literally going to be like the one I showed you the other day, just instead of having plus 1, it's going to be plus h prime of k all mod m, like this. So it's h prime of k right here. And then I just increment c just like before. And then I just have if c is equal to m, then return error, right? Because I couldn't insert it properly, correct? Okay. We end the while loop, and then I just simply perform the insertion. Remember, so I really haven't changed a whole lot. Remember, the secondary hash function can compute it in constant time. So all your complexity results that you know for linear probing are the same here. So just a reminder, this takes worst case linear time, just like it did in linear probing. So I'm just going to mention that since h prime of k takes constant time, worst case. So in the worst case, its analysis is the same as linear probing. So you can tell really fast that the algorithms for the other operations are going to be just the same as we had before. Just replace the line you have for get and remove. You would just replace it with this instead of just the +1. Okay? And you get the same asymptotics. So I want to talk about why this property has to hold. The fact that Q is prime and M are prime. So I'm going to illustrate it with an example. So let's do an example. I want to illustrate why this is very important for double hashing. Okay, I'm going to create a table, and I'm going to disobey my instructions, and I'm going to make the table M, capital M, be 8. So remember, 8 is not a prime number. 6, 7, that's T. So my hash function is going to be K mod 8. K mod 8. And my secondary hash function is going to be h prime of k, which is going to be 7 minus k mod 7. So that's going to be my secondary hash function. 7 is indeed a prime number, right? So I'm going to just not take my advice, and I'm just going to try using this. Just for the sake of time, I'm going to ignore the null references. Okay, I'm going to try putting in h of 2. So I'm going to assume I'm going to put the record with value 2 in. Where should it go? Well, the function says, okay, well, my hash is I'm going to hash into position 2 because 2 mod 8 is 2. So I just put it right here, right? Goes right there. Really easy. Okay, how about h of 6? Okay, 6 is pretty easy, right? By the way, that's 2. This is 6. Goes in here. Is everybody following me so far? So I have these two. How about this? Now, this is going to be a little bit funky. I'm going to try to put in 10. So the record's key is a value 10. I'm going to attempt to put it in. Now, what's 10 mod 8? It's 2. Think of it as, okay, well, what's 8 mod 8? That's 0. 9 mod 8 must be 1. Then 10 mod 8 must be 2. So that's 2. So I attempt to put it right here. So what does that mean? That means I have to now apply the secondary hash function to get my offset. That little jump. Remember the rocket boots on my bunny. So what's h prime of 10? H prime of 10 is going to be 7 minus 10 mod 7. So that's going to be equal to, okay, 10 mod 7. So what's 7 mod 7? 0. What's 8 mod 7? 1. 9 mod 7 is 2. 10 mod 7 is 3. So we got 7 minus 3 is equal to 4, right? So now I'm going to be forming offsets by 4. So now, if you're really clever, you can look at this table and see quite quickly what's going to go wrong here. But I'm going to work it out for you. Okay, so if I get a collision here, what am I supposed to do? I'm supposed to take the hash function plus a multiple of the secondary hash function's result. So let's see. So I got 2 plus, so it's 1 times the secondary hash function's result, mod 8. What is that? That's 6. Okay, what's So it jumps down. Okay, so I get a collision here. I jump down to 6. Okay, so that's 6. We get a collision again. So I'm supposed to, according to the double hashing scheme, I'm supposed to go 2 times 4 here. So remember, h of k plus 2 times h prime of k, mod 8. Okay, what's this? 2 plus 8, that's 10, right? Well, what's 10 mod 8? What's 10 mod 8? That's 2. Okay, so you gotta think of it like, okay, well, I kind of, I'm going around. Okay, I have returned back to 2. I've wrapped around. Okay, how about this? 3 times 4. Okay, 3 times 4 is 12, plus 2 is 14. Okay, so what's 14 mod 8? 14 mod 8. So I've got 12 plus 2, 8. So, okay, well, what's 12 mod 8? Okay, that's 4. So 14 mod 8 must be 6. So, well, okay. I'm back to 6. Okay, let's just make sure. Let's go 2 times 4 times 4 mod 8. Okay, we got 16 plus 8. That's 18. Mod 8, that is 2. Okay, I have gone all the way around, and my hops, these are quite the rocket boots. They're able to circumvent the whole orbit of this table. But you'll notice that the bunny's never really going to get anywhere. It's never going to find that nest. In fact, this pattern is going to keep going and on and on and on. It's never really going to end, and 10 is never going to get stored. So it's never going to get stored. Oops! That's going to be a problem. So I want you to think about why that might be. So one big thing that we took advantage of was that the table size is prime, and we know Q is prime, so we know we always take a jump, which is true. We do take jumps here. Every time we don't have 0. However, there's also this other thing in play, right? Now, for those that know a little bit about number theory, you might know a little bit about modular arithmetic. Without getting into too many details, I'm going to explain why this works when you have them both being prime. So I'm going to define what is called relatively prime. Sometimes this is called coprime. So relatively prime or coprime. So we say that 2 integers, these are going to be 2 integers if they're only positive integer factors. You might know the more technical phrase, it's called divisors. It's divisors. 2 integers if they're only positive integer factor divisors that divide both numbers are 1. Are or is, by the way I phrase this. So basically, if I give you 2 numbers, the only divisor that they're going to have in common is going to be 1. So if I give you 2 integers, like P and Q, and I tell you, okay, well, are they relatively prime? The way you tell me is if they're factors or divisors, it's only 1. So just as an example, if I consider integers 3 and 8, these are relatively prime. These are relatively prime as the divisors of 3 are what? 3 is a prime number, so it's 1 and 3, right? How about the divisors? The divisors of 8 are 1, 2, 4, and 8. Which one do they have in common? Just 1. Okay, so there's a lovely property that M and H, so that M and H prime of K must be a relatively prime. So I will not prove this for you. And if so, then the whole table can be explored. So meaning, if you know this in number theoretic terms, it means that there's a period for this computation, and it has a certain length, and I'm not going to get into those details, but the point is that if this is not true, it's very possible that you won't explore the entire table. Otherwise, it might not. It might not be explored. Like in the example. My writing is just being all funky right at the moment. So, like in the example. Okay. So, just the big thing you got to keep in mind with double hashing is that M and Q should be relatively prime. What's an easy way to make them relatively prime? Just make sure they're both prime numbers. Because by definition, M, if it's a prime number, its divisors are 1 and itself, and Q is less than M. So you can guarantee if you give Q as a prime number, it will not be one of any of those divisors of the other prime number. Does everybody see that? So that's why double hashing will work in this way. So if we don't have that, we don't have a guarantee that we're not going to run into a situation where it's never going to terminate. This is why termination matters. Does everybody see that? So it's very possible that if I give you the wrong M and wrong Q, that function I showed you earlier, that get method, will not actually ever terminate. Which is kind of weird to think about, but it's a very real possibility. Okay, so what we're going to do next is we're going to revisit the load factor. I promised I was going to talk a little bit about average numbers of collisions. So let's talk a little bit about that. So we're done talking about double hashing. So I'm going to revisit, so revisiting the load factor. So we're revisiting the load factor. So we can implement, so this is the big takeaway from hashing, is the following. We can implement all the main dictionary operations in big O of 1 average time under under our assumptions. So remember, we're talking about the assumption that the keys are uniformly distributed by a sufficiently good hash function, and those keys are being provided over a distribution such that they're going to be uniformly distributed over the table. Think of it like I have a piece of bagel, and what I want to do is I want to spread the butter across the whole side of the bagel. So I'm making that assumption. I'm assuming it's random, basically, a uniformly random distribution that I'm being provided, and a sufficiently good hash function. Okay. So what we're going to do is we're going to be a bit more specific. Let us be a bit more specific about the average number of comparisons for the get operation. We're going to see that the load factor actually plays a role in this, which is quite fascinating. So I'm going to make a hopefully okay looking chart. I advise you look at the notes. But you should be able to get the gist of this, say if I were to ask you about this. Okay. So let me do a plot for you. So the first one, so the vertical axis is going to be time. You can also think of this as the number of comparisons, which that characterizes the time complexity in get. And we have the load factor. So the load factor is going to be 0, 0.5, and 1. So remember, this is the load factor on horizontal. So this is alpha. Remember, alpha is equal to n over m, where capital M is the size of the table, n is the number of records in the table. So what I want to do is I just want to plot these out for you. So if I were to consider the number of comparisons I do, depending on which collision resolution I select, it will look something like this. Now, I've deliberately left this unlabeled because I just want you to get the general gist of the patterns. You can actually calculate them out if you'd like to. I'm going to give you the actual numbers. Okay, so if you're looking at separate chaining, it will look something like this. So that shows to be a straight line, by the way. So this is separate chaining here. So separate chaining is right here. That's supposed to be a straight line. I really should have pulled up my meter stick for this. Then, the way you're going to see this is that around right about, say right about here, you're going to find that it's going to have this for linear probing. And double hashing is going to be somewhere about the middle. So this is double hashing here. Okay, so this is a plot out of the average number of comparisons for the get operation I would do depending on the load factor. So the load factor is controlling the horizontal axes here. This should be natural that that's a straight line because we've already talked about what the load factor looks like in relation to separate chaining. So I'm going to make a little table here. So collision resolution, and then the second column will be the average number of key comparisons. Okay, so for separate chaining, for separate chaining, we already talked about this. It's 1 plus alpha. Remember I told you that the average case time complexity is big O 1 plus alpha. The average number of key comparisons is 1 plus alpha, by the way. Now remember, just remember my analogy with the cake. I layer the cake and I put icing in between. I spread the icing uniformly across the layer of the cake. I do this every single time. How many times are going to have to layer uniformly across the cake? It's dependent on alpha, right? So the more items I put in, the more it's going to stack up like this, but it's going to be uniformly spread in the average case, okay? Okay, linear probing. So this is where it's going to look a little strange. And I'm not going to calculate this out for you because I don't know if we have everybody having the sufficient level of mathematics for me to pull this out. However, I'm certain that if you go looking around, I'm sure you can find the analyses for this. So it's actually 1/2 plus 1 over 2 times 1 minus alpha squared. Okay, double hashing. This is much simpler. 1 minus 1 over alpha. So notice that if the load factor is basically close to 0, you're going to end up with roughly 1. If it's close to, if you'll notice that if the load factor approaches 1, you're going to end up with something that's going to get, you're going to notice very quickly that this is, if this is close to 1, then you're going to get 1 over something that's kind of like a little wild. But the point is that if you fix these alphas, you're going to end up with constant time. So I already see that. So if you decide on an appropriate value for alpha, you're okay. You're going to get all these nice results here. So I'm just going to talk about what this would mean in terms of practical terms. So in linear probing, I want to talk about rehashing. Remember, rehashing, I mean you take all the records in the table, you're going to build a brand new table that's bigger, and you're going to rehash, meaning that you're going to take each one of the records, put it into the table. It's a very expensive operation. So I want to give you a rough estimate of when might be a good time practically before this curve starts getting out of hand. I'm going to roughly say, okay, well, I'll rehash if alpha exceeds, I would say approximately 0.35 to 0.45. And for double hashing, you might want to, rehash if alpha exceeds approximately 0.5 to 0.6. So keep in mind how much space you have for your application. So you might not necessarily have the ability to rehash nicely, okay? So these are just some rough measures, just based on what these look like. Because remember, you don't want to let them get too out of hand. Because you would agree with me that if I end up with something that's getting really, really small in the bottom on this one, it can get very out of hand. But the point is that for some alpha, it's going to be constant, okay? And we already talked about separate chaining. Remember, separate chaining, the whole idea is that I fix some constant for alpha, or at least the idea of alpha, and you just keep the size of the table in relation to this load factor. So you think about how big your table needs to be, roughly how many key comparisons on average you'll be okay with, and that's how you can gauge how big the table should be for separate chaining. So this answers the question for open addressing of how big the table should be. So, you know, in double hashing, that must be prime. Linear probing doesn't have to be, but in practice it typically is. And just keep in mind the average number of key comparisons. So with my last bit of time on hashing, I'm going to talk briefly about where things go from here. because we're not going to talk too much more about hashing. So beyond this course, so there's some things I just want you to be aware of if ever you find yourself interested in digging into these things, or if you take a cryptography class that includes hashing, or some security class. Sometimes they talk about hashing in that kind of class. Regardless, you'll probably encounter hashing sometime in your future if you're curious about this kind of stuff. Okay, hashing is extensively studied. That's the big thing I need you to be aware of. It still is a very much an active thing. Next, there do exist hashing functions with no collisions. So they can guarantee you no collisions, which is quite weird to think about. Requiring. Now I'll put quotation marks with the no, because technically this process is a type of collision resolution, but not in the way that we're talking about. You can easily adapt it with these kind of things as well, though. That's the good thing about it. So I'll say they are called perfect hash functions. So if you're curious more about that, you can always take a look into perfect hash functions. In addition, now it's worth noting that one of the drawbacks of these approaches that we've talked about is in the worst case, they take big O of n time, right? I want to address that. There has been work in maybe the last few decades on things like this. In addition, there are types of hashing that support worst case big O of 1, so constant time, get operations. This includes what is called cuckoo hashing. So if you're curious about that, just look at the cuckoo hashing. The big idea with cuckoo hashing is, if you ever heard of the cuckoo bird, I recommend looking into the nesting habits of the cuckoo bird. You'll learn the basic idea of what cuckoo hashing is about from looking into something like that. It's very much the metaphor that applies for that type of hashing. Okay, so this is basically where I'm going to end off when I talk about hashing. So remember, the big perk here was that we were able to get down those average case time complexities from where we didn't have to worry so much about these worst case scenarios so often. But now we have something that you can actually, if you expand a lot more extra memory sometimes, depending on how much memory you want to use, you can actually get average case constant time operations, assuming you have a good hash function. Okay? So let's talk about something else, because I got enough time to do that. We're going to switch gears quite dramatically. We're going to talk about trees. Yes, trees. Not the trees outside, though. We're not talking about those trees. I know I've been talking about rabbits and all sorts of other things. I'm not talking about literal trees. So, a tree is an abstract model of a hierarchical. Always have fun spelling hierarchical. Sometimes where that I needs to go goes into a funny place. Hierarchical structure. So trees are an example of something called a graph, which we'll talk about those later on in the course, okay? But these are a way you can model hierarchical structure. So just some natural things you can think about as hierarchies. Some examples include, so you might think of a file system. File systems are organized like trees. How can you verify this? Well, just look at your operating system, look at your file explorer. Your computer is broken up generally in terms of drives, which all follow from your entire system's memory. And then what happens is you have your drives, they get broken up into folders, and your folders are broken up into directories, subdirectories, and so on. Okay? So that's what I mean by a file system. Seems very natural. Another way you can think about it is an organization of a company. So imagine I give you some company, it naturally can be organized like a hierarchy. So I'll give you a fun example. I'll call the company Compute and Company, because that's totally an original name. I better trademark that. Computing Company. Get it? Because it has an and. But it's Computing Company. Okay, so this might be broken up into 3 divisions. Sales, manufacturing, and research. So it might have 3 divisions. Now, in the manufacturing division, they might be interested in kind of 2 sectors. They might be interested in laptop and desktops. So there might be, this company might manufacture laptops and desktops. Now, the sales division, it's probably broken up in something like Canada and international. Now, don't question me on this, because this is a fictional company. I don't know how they operate, okay? So they're going to have some business partners across from in other places in the world. They will include the USA. International trade partners are the UK, so they do business internationally with USA, the UK, and Candyland. I've confirmed for you, by the way, the Computing Company does, in fact, know where Candyland actually exists. Okay? So, anyways, let's talk about some tree terminology, and I think when we're done doing that, that'll conclude today's lesson. So, we're going to talk about what some tree terminology means. So, when I talk about trees, this is going to be the language I very often will use. Okay. So I'm going to write down tree terminology. So it's worth noting that you probably know a little bit about trees already. If not, you're going to be just fine. So we're going to be talking specifically in this course a lot about rooted trees. A rooted tree is given below. So I'm going to draw you a rooted tree. It's going to look like this. So I'm going to have A here. It's going to have 3 coming off here. B, C, and D. Then below C are going to be G and H. G and H. And below B are going to be E and F. And then from below F are going to be I, J, and K. Okay, so this is my rooted tree. The reason why I call it a rooted tree is because I've designated a node as a root. So this is called the rooted or root node. And just to be consistent with what I'm going to talk about later in this course, I'll say rooted node or vertex. Now, any one of these, including the root, are all called a node or vertex. A node or a vertex. And each one of these guys, these connectors that are kind of going into the cube like vertex or nodes, each one of these are called an edge. Sometimes in some scenarios they're called a link or an arc. Usually this is to indicate that it has no partial direction. A link oftentimes is a synonym. An arc usually indicates it has some direction. But it depends very much on the context for which they're using it. So that's a tree right there. So remember, rooted trees have a root that's designated. And then we have the tree consisting of nodes. Those are what all those circles over there are. And the things connecting the nodes are called edges. I'm going to lay out a whole bunch of tree terminology the last about 5 minutes we've got. So the big thing I want you to observe is that nodes have a parent-child relationship. So in a tree, they have a parent-child relationship. So just to make my terminology a little bit clearer, I'm going to illustrate some examples along with defining the terms implicitly by doing so. Because I think it's more fun when I do it that way. Okay. So if I look at my picture over there, which one was the root again? A was. A is the root node. Typically in a rooted tree, you assume that it only has one root. Okay, how about B? I'm going to say B. Now I want you to look at this node here. The one's below it. So you got to look at it as the root and everything splays away from the root. Okay, if B's here and there's these two below it, these are called the children of B. So what does that mean? If E and F, whose parent are these in the parent-child relationship? It's B, right? So B is the parent of E and F. Now, oftentimes when you have two children, or two or more children that belong to the same parent, they have the same parent, we call these siblings. You're going to find we're very much going to use a familiar kind of a familial type of language to describe this. C is the sibling of B and D. So notice that the parent of B is A, but C's parent is also A, and D's parent is also A. So C, B, and D are all siblings. Okay, B, C, and D are children of A. The point is that they're directly children, right? This isn't some weird metaphor where all of a sudden all the ones below it are also their children as well. We're not doing that. We're saying they're direct descendant. However, not to be confused with this term, So E, F, I, J, K. So if I look at E, F, I, J, and K, these are all descendants. So these are our descendants. Are descendants of B. So this is the distinction. Children, they have a parent, they're the child of that parent. Descendants, this includes everybody after that parent. So I have this node, all the ones that follow below that follow from a child relationship beyond B. So all of the ones below here, these are all descendants of B. Because at some point, their parent was a child of B. Okay? Okay, how about A, B, and F? Now A, B, and F. So let's see, A, B, and F. So A, B, and F. These are all preceding parents or some ancestor to any one of these three down here. So we'd refer to A, B, or F. These three are ancestors of J. And it's worth noting that A has no ancestors. Why? Because it's the root. Likewise, you should also mention with the descendants, all nodes except A are descendants of A. Why? Because it's the root. Okay, so I have a few more terms to lay out here. So let me just quickly do that. I have just enough time, I think, to pull it off. Okay. So I'm going to define what an internal node is. So an internal node is simply a node with at least one child. Okay, can somebody point out to me an internal node here? Okay, is A an internal node? Yes, because it has 3 children. Okay, how about B? B is? C is? D isn't because it has no children. And then we have lastly F, right? F has children. So example, A, B, C, F. Okay, that in contrast gives me an external, describe what I call an external node, or what I prefer calling it, a leaf or leaf. This is a node with no children. I want you to think about over there, give me a child, a node with no children. E is one of these. So in fact, E, I, J, K, G, H, and D are all leaves. So one thing that actually it's worth mentioning is that the plural of node is nodes and the plural of vertex is vertices. We'll talk more about vertices in that context later, but I just feel like I need to point that out. So the plural of leaf is leaves. Think of leaves off of tree, okay? So the depth or level of a node. So this concept is going to be fairly important for us in this course. The depth or level of a node is the number of ancestors. It's the number of ancestors. So for example, if I look at E, how many ancestors does E have? 1 and 2. Example, E has depth 2. Okay. So the height of a tree is the following. It's the maximum depth of any node. So if I give you the tree, what would be the height of this tree? Well, it's the maximum depth. So what's the maximum number of ancestors somebody can have? Well, it's 1, 2, 3. Any one of these would have been sufficient to compute the maximum depth. So the tree has height 3. Okay, I have 3 more terms. I got a couple minutes before, so let me quickly lay those out, and then we're going to wrap things up. I apologize. Okay, a subtree. So if I okay, so a subtree is a tree consisting of a node and its descendants. Okay, so for example, if I consider F, this would be the subtree of F. So if I pick F, the tree consists of it and all of its descendants. Likewise, if I pick just D, the subtree would just be D. If I pick A, it's the entire tree. So naturally, you're going to see that our trees have a very nice recursive structure where trees can actually be composed of subtrees. So I can take all the subtrees and I can assemble the entire tree. So we're going to find that very often our algorithms are going to take advantage of this property of a tree. So an ordered tree the children of the nodes are ordered. So they're ordered. So notice that so if I look at my children of A, they're listed in order from B, C, D. Notice that they're ordered and they're all in order, right? However, if I were to switch G and H, that would make them out of order. So the children of H. So for example, if I was measuring this over the alphabet, this would be an ordered tree. In the sense that if I was measuring how ordered it is in terms of the levels. Keep in mind that isn't the only definition of what an ordered tree might be. I'll be giving you a more particular definition of what an ordered tree would look like later on. So, like I said, this is a very wishy-washy definition. We'll have a more precise one later on. So this is just naturally that the children, as everything's the same here, except for unordered. Like I said, if I switch around G and H, this would make this tree unordered. Okay? So that wraps up all the main tree terminology I wanted to talk about. Next day, I'll start off with talking about the ADT for a tree, and then we're going to talk about what we can do with a tree and some properties they have. Okay? So thank you very much, and have yourself a beautiful day.